Fundamentals of Geology. Today we're going to talk about principles or laws of geology. This is a two-part series. I will leave a link to the first part in the description. So let's look into this. So fundamentals of geology, as I mentioned before, is related to relative dating. It's mostly based on relative dating, as I mentioned before. The idea behind relative dating methods are as old as the geology itself. In modern day geology, we no longer accept the theory of catastrophism. Instead, we know that the Earth and its geology has been evolving over a long period of time. To understand these evolutionary processes, we use the following principles, which is directly linked to relative dating. In my first video, I discussed principle of uniformitarianism, law of superposition, principle of original horizontality, principle of lateral continuity, principle of cross-cutting relationships. And today we're going to discuss principle of fossil or faunal succession, principle of intrusive relationships, and the law of included fragments. Let's start with principle of faunal succession. Principle of faunal succession is also known as principle of fossil succession or law of faunal or fossil succession. And it is based on the idea that the plants and animals preserved in the rock record can be used to interpret the geological history which the rock or strata has been deposited. It is part of the biostratigraphy. Biostratigraphy is a branch of stratigraphy which focuses on correlating and assigning relative ages of the rock or strata using fossil assemblages contained within them. Basically, if you find a certain type of fossils in a certain strata, and you can use the history of the fossil to identify the history of the geological processes and the rock layer itself. It was first introduced by the English geologist William Smith, and he used the concept for relative dating of rock strata in England. After he introduced this principle, a French naturalist and zoologist, Georges Cuvier, popularized the principle by publishing another research paper, and he was able to analyze the strata from Britain and France and link them together to common geologic periods, thus born the idea that certain types of fossils existed for a specific period of time in Earth history, and that layers of rocks bearing these fossils could be correlated across the countries, across vast areas of land, or underneath the land in this case. So William Smith introduced the idea in United Kingdom or England, and then George Cuvier popularized the idea later with his studies by correlating the strata in France and United Kingdom. So what are the key features of fossils or faunal succession? Typically, when we are looking for fossils, we are looking for fossils that are characterized by short lifespan. The reason being, if a fossil is spanning across millions of years, it will cut across multiple geological time periods. Hence, having a shorter lifespan fossils can be a very useful tool to identify specific periods of geologic history. For example, imagine somebody to live 10 years. During that 10-year period, that environment may have changed very little compared to somebody who lived 80 years. In terms of human terms, the environment and society and everything changed dramatically during that period because everything changed over a period of time. So having a short lifespan compared to long lifespan we can use those fossils as identifiers or markers of certain geologic time periods or historical periods in the rock record. And another feature that we are looking for is fossils that have a wide distribution. So the fossils that we can find in multiple different continents, spanning across multiple different regions, are very useful. For example, if you can find the exact same fossil in Alberta, Canada, as in let's say London, England, that can be very useful to correlating stratigraphy across the earth. In fact, we have used some fossils from Alberta, Canada to correlate geologic layers in places like in China, which give you an idea about global climate and global geological record. And we can study the history through wide distribution of these similar or same type of species. Third feature that we would look for is a distinctive identifiable features. So some species may look similar to another species, but however, if we can find distinctive features between each species, we can use that as a tool to identify specific species and link them to a specific period of geologic history. And you also need to understand that not all species will undergo extinction or changes to their characteristics during a major geologic event. So not all species can be used as identifiable markers. As a scientist, you have to pick the correct species that undergo major evolutionary changes or extinction in order for you to understand the history of the earth. So remember, sometimes some species will undergo long evolutionary change. It may be useful sometimes when it is preserved in a rock record, but typically it is very useful when species, for example, disappear after a major geologic event, or a new species appears after a major geologic event, because that can be used as one of the boundary markers between different periods of time. So the fossil assemblage or faunal assemblage are groups of fossils that found together in strata or rock. Basically, they are associated with each other. You can think of it as a set of fossils that are grouped together based on common time period, characteristics, and depositional environment. Different types of fossils within a given assemblage are often found together. An example of this would be in this particular diagram. These type of fossils together will only be found in layer number 11. You're not going to find it in layer number 9 because it's completely different types of assemblage. You may find this fossil or similar types of fossil in layer number 9 and 7. However, this particular assemblage, that means combination of this fossil and that fossil, will not be found in layer number 7 because it has a different assemblage. So you can identify, even though this fossil, imagine if this is the same fossil as this one, even though this fossil survived all the way to layer number 9, other fossils did not. So using assemblage, you can interpret that geologic history of this layer is different from geologic history of that layer. So that's pretty much the basic idea of fossil assemblage. So instead of using a single fossil to identify a period of time in geologic history, you can use multiple associated fossils or layers of material to identify different time in geologic history. So the next thing is diagnostic fossils or species. Basically, diagnostic fossils or species have several characteristics. It appears or disappears from the fossil record at a critical time in geologic history, or it has a fast rate of change in characteristics compared to all the other fossils. So basically what that means is that a particular type of fossil will appear in a certain rock layer. For example, this fossil is nowhere to be found anywhere here and anywhere up here. So it appear and disappear within this particular geologic time. Now that's a very good diagnostic fossil for rock layer number 9. And they're very useful because it can keep, like it can be used to constrain the geologic record history, and it can be used to identify specific layers of rocks across a wide area, for example between China and Canada. And the faunal succession can be used to determine both evolutionary and catastrophic changes in geologic history spanning back to millions of years. It is a very useful tool for analyzing environmental conditions, biodiversity, and geological conditions. And this particular diagram, it shows different layers of rocks being deposited on top of each other, and you can see some of these fossils appear on the both side of this diagram. So imagine this is hundreds of miles away, and maybe a river cut across this or something happened in between, or this could be two different countries. This could be Canada and this could be China or United Kingdom. But because this particular fossil with this particular feature appear in the rock record in this period, and we find the similar fossils in China or some other country, and you also see the layer beneath it have a similar fossil again on both sides, we can use that to correlate laterally across a wide area. In other words, this layer number 4 must be the same layer as this layer number 4 and must have been deposited at the same time. Now sometimes we don't find the layers on both sides of the equation, both sides of the widespread areas. This may be due to erosional events. For example, rock layer number 5 with this particular fossil does not appear on the other side, but maybe there was an erosional event. So we will interpret that as an erosional event that that caused that layer to disappear. That because when you have wide distribution of geologic material, the environment is not always the same across the board, but however the period would be the same. So this fossil may have lived in this particular area too, maybe not, maybe the environment is slightly different, but the record is no longer there. So this is one of the key features in faunal succession. So as I mentioned multiple times, the principle of fossil or faunal succession is based on the fossil record. The paleobiological hierarchy or the paleobiological history is a methodology that we use to identify fossils and associated them with specific period of geologic history. How we do this is we study rock samples or rock layers with fossils embedded within them, and we can draw conclusions based on the information we have, the period which the organism lived. So based on that data, we can correlate hundreds of fossils with different ages of the geologic history. In this particular chart, for example, I put few fossils or organisms on the x-axis, and I put the different ages of geologic history on the y-axis. Then I placed these columns with colored, with blue color, showing which period, each and one of these organisms lived. And some of these fossils can be very useful. For example, this particular fossil up here, you can see that fossil only lived in Cretaceous period, because we only found this fossil in the Cretaceous rock record, and that can be a very useful key identifiable fossil. Here's another one, for example. And some of these fossils have lived for a long period of time, like this fossil, for example, spanning across multiple geological periods. These fossils can be useful as well, because most of these species undergo evolutionary change, and we can study these species along with the rock record, not only for identifying different rock layers and their periods of time, but also how these species adapted to the changing environment. So there's two things you need to remember. The species that only appear and disappear in a fairly quick period of geological period can be used as a key fossils, and the species that live long across multiple generations, multiple geologic periods, can be used to understand the evolutionary change through the geologic time. If you would like to learn more about paleobiological hierarchy, you can visit my website right here. I will leave a link in the description, or you can search it on Google as well. So the next thing we're going to look at is called the principle of intrusive relationships. Typically, the principle of intrusive relationships are associated with igneous intrusions, and it is directly or indirectly related to principle of cross-cutting relationships. And we learn about cross-cutting relationships in my first video. Again, I will leave a link in the description. You can check that out. And it is the relationship between the country rock and the intrusion. So we can interpret the history of the rock record based on the intrusive material that cut across the country rock itself. And there are different types of intrusions that you're gonna find in the field. I will make a separate video on types of intrusions, but for now, what you need to remember is that typically principle of intrusive relationships are associated with igneous intrusions. So different types of intrusions, you can see some of them here, like for example dike, sill, for example. And in this particular picture, this is a dike. So this is a country rock and this is a igneous dike. So the dike is younger compared to the country rock surrounding it. So these dikes can spread meters to kilometers in for an area. Like I put a hammer when I took the picture, so you can see the size of the dike. You can get an idea about the size, but they can be small like this, or they could be very large as well. So differences between these different types of intrusions, again, I will talk in a different video. And for now, just remember it's kind of a relationship between the country rock and the intrusive body. Remember the principle of cross-cutting relationships? If you don't, you can view the first part of the video as I mentioned before to learn a little bit more or freshen up your memory. Basic principle behind it is if a body or discontinuity cuts across a stratum, it must have formed after that stratum. So imagine you have different layers of rocks being deposited. So I created this model of that scenario using the visible geology, and again I will leave a link in the description. So when the rock record gets formed, it pretty much formed pretty horizontally, but things happen after that because geology is an evolutionary change with some catastrophic events. So take some time, and you may want to pause this video and see if you can determine which one of these events occurred at what period of time. In other words, what is the sequence of events in terms of deposition of all these rock layers. And this is a dike, this is a dike, and this is a normal fault. So take the time and think about how this particular geologic block is formed. You can pause the video. So those who really want to know the answer, I will go ahead and continue. So based on this diagram, all the layers of strata were deposited first. So this green layer all the way to this brown layer and everything in between got deposited first. We know this because this fault have cut across every single one of these layers. So does this dike and this dike. You can see from here and here as well. Then the dike in black cut across the strata before the normal fault was come about. We know this because this dike have been offset by this normal fault. You can see that this dike goes straight through and then suddenly it become offset right here. Then the dike in brown, this dike formed next because it cut across even the normal fault itself and it does not have an offset. So the intrusive relationships basically shows the interaction between the intrusive bodies such as these dikes and the geologic rocks that been deposited, or in this case even the normal fault. So this dike actually much younger than the fault itself as well. Here's another diagram of intrusive relationships. So you can see some sills and dikes, and again I will explain what's the difference between every one of these later. So typically what happens is this is all country rock and there are different layers of different types of rocks in the country rock, and an igneous body would intrude into the country rock which resulted in an intrusive relationships. And these type of intrusions are not only important in terms of identifying sequence of events, but also sometimes these intrusions bring rock samples from deep beneath the earth, which we would not be able to study otherwise, because it's like hundreds of thousands of meters to kilometers underground. So the next law we're going to talk about is the law of included fragments. The Charles Lyell introduced the concept with the 3-volume publication titled Principle of Geology between 1830 to 1833. As we learned before in the previous video, he also introduced the principle of uniformitarianism. And the basic idea behind the law of included fragments is that clasts in a rock are older than the rock itself. And sometimes it is related to igneous intrusions as well. So let's look into this as well. So the clasts in a rock are older than the rock itself. So that's the basic fundamental idea. Typically, these clasts are sedimentary rocks. So for example, in this rock, these are clasts of rocks and they are typically sedimentary rocks. And these foreign bodies are incorporated into the rock itself. So this is the rock itself, and these clasts or foreign bodies are incorporated into the rock itself. As I mentioned before, sometimes often they are related to igneous events, such as the magma and lava which travels through the country rock or the surface of the earth typically can pick up these sedimentary particles and incorporated into its structure while it cools down, forming rocks. So just like igneous intrusions cut across country rock, those igneous intrusions can pick up sedimentary rock particles from the surrounding area, which resulted in these included fragments. So in this particular image, you can see this is an included fragment, this is another fragment, you can see another fragment here and another fragment here and another fragment here, and some of these fragments have the exact same age, while other fragments have different ages. So the rock has a younger age and these fragments have much older age, but however some of these fragments are related to each other, so from the similar time period, while the others could be completely different time periods. So the law of included fragments basically state that when you have a rock with fragments within them, you can study each and individual fragment to understand the history of not only the rock itself, but also the fragments contained within them. And typically we will see classed such as gravel or large fragments incorporated into these rocks. And that's everything for today. If you would like to learn more about geology, more than welcome to visit my website at sanuja.com. At the end of this lecture series, you should be able to practice your knowledge on this particular page, and I will leave the link in the description. You can also check out my other exams which are posted under this page. If you have any questions, feel free to contact, and please subscribe. Have a nice day.